until we start to get somewhere, but a probability function, mass function for a discrete random variable, okay, is a probability mass function. P of x, okay, is valid or must conform to our axioms of probability, okay, must conform to our axioms, right? So, in particular, two things, okay, one, for all x, you can't have a negative probability, so your probability has to be at least 0 for all x. For all x, okay, okay, and by the way, this will be a source of confusion a little bit early on until you get used to it. You're gonna see sometimes I'm using a capital letter, right? And sometimes I'm using a lowercase letter, okay? Capital letter refers to the random variable as a function. The little x is one of those possible values, probably in its range, right? So you'll see us say things like, what's the probability capital X is equal to 2, right? Or you might hear us try to generalize that equation. What's the probability capital X is equal to little x, right? Okay, and so, one, the probabilities can't be negative, and two, the sum of the probabilities across all x in the range of x. You see what I mean? My lowercase, my uppercase, okay, must add up to 1. Those are the two conditions that make a probability function valid, okay? Probability mass function. Next up, in general, don't forget what we're doing with all random variables, but in this context, a discrete random variable is we're codifying, we're numerically assigning a number. We're assigning a number to each of the outcomes, so thus we're creating a partition of all those outcomes based on the number, right? And so, let's see if I can write this.
So for the sake of note clarity, curly x is little x.
Curly x is little x.
Okay, thank you.
Yeah. Curly versus boxy. Okay, and so, let's see. It will be the truth for discrete random variables. For a discrete random variable, call it x, okay? Little p of x, or little, these are little p's, that's okay, is the probability that random variable x takes on that little value x, right? And that is the sum across all the outcomes in omega such that x of omega is equal to little x, okay, of the probabilities on omega, okay, right? Again, this is just kind of fine-tuning what's there. You'll see this go into action, okay, in just a second. It's like the doing, well, we'll see, okay? A probability distribution, distribution is a table or a rule that lists all values for that random variable, and the probability associated with each. Okay, and so, a little bit of new notation, but kind of the same old theme, and I know we are gonna be done with coins and dice sometime soon here, but let me just do one more example of these so that you see what I mean. And so, let's simply flip a coin. Let's flip, I always wanna roll my coins. Flip a coin. Let's just do it. How many times do you want to do it? Small. 3 times. 3 times. Let x be the number of times it lands on heads. Right? Don't forget, in my sample space, my sample space is tail, 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 head. How many outcomes in this sample space? Tail.
Is it 8? And to the 3.
Head, tail, head. Three stages, 2 possibilities per stage, 2 to the third out, 2 to the third would be the total number of outcomes. Did I list 8 there? It looks like I listed 8 there, right? You'll notice by this that x is the number of times it lands on heads, right? So this is x equals 0. These 3 events correspond to x is equal to 1. These 3 events correspond to x is equal to 2. This corresponds to x is equal to 3. Right? See what I mean when I say that a random variable by nature partitions a sample space, right? And so the probability distribution right? Let's list x, let's list the probability of each, right? And x can take on a 0, 1, 2, or 3, right? See how we have kind of already moved away from that function notation on the random variable itself? Do we like this so far? Right? By the way, we're going back to kind of day 1 probability. These are equally likely outcomes, right? So what is the probability that x is equal to 0?
1 over 8.
1 out of 8, right? And the probability that x is equal to 1, are you all in agreement? That looks like a 3/8.
Mm-hmm.
Probability x is equal to 2 is another 3/8. Probability x is equal to 3, there's only one way that can happen, 1/8, right? Did we produce a valid probability distribution? Are all the probabilities non-negative, and do they sum to 1 across all the possibilities? Yes, indeed they do. Okay, so this is a valid probability distribution. Okay, there we go. Okay, we check it adds up to 1. Fantastic. And so we see that for this particular distribution, right, x can take on, I'll offset the 0, a 1, a 2, or a 3 in this case, and the probability is 1/8, 2/8, 3/8, probability distribution looks like
The bell curve.
kind of the start of it, isn't it? Right? Right? How's that feel? Does that seem okay? You see that probability distribution. And now, by the way, you say you can start, there are other things we can ask. Now, so far in this course, all we've ever cared about is probabilities, right? Right? But it's a vast world, okay? And so now you're gonna see our concentration be split kind of two ways. One is probabilities, calculating probabilities on the particular values of x, right? Another way, another point of interest is this distribution. Let's look at the big picture of that distribution. Now that we've turned it out, now that we're describing outcomes as numbers, we can ask questions that we couldn't ask before. On average, if I toss a coin 3 times, how many times will it land on heads? Right? Right? That's a computation we could now discuss, right? One time I toss 3 coins and I get no heads. Another time I toss 3 coins, I get 2 heads. Another time I get 1 head. Another time I get 2 heads. Every time I try this experiment, tossing the coin 3 times, there's variation in what I might observe. 0 heads, 1 head, 2 heads, or 3 heads, right? Can we quantify that variation? Yes. We know of it as things like the variance and the standard deviation are measures of variation in a distribution, right? Right? So you see how as soon as we took those outcomes and those events and we codified them numerically, there's a whole wealth of more information we can garner from that, right? Right? And so we look at this distribution, okay? And some questions we might ask ourselves are things like, where is the center of this data set? You know, on average, how many heads would you observe in 3 tosses? Okay, how much variation is there in a distribution? For instance, you know, if I told you on average when you're graduating, the average ECE major gets a job and earns, I don't know what, $70,000 a year. You know, that's nice information, right? What if I told you that you know, on average you earn $70,000 and the range is between 65 and 75? That paints a picture in your head. What if I told you the average was 75? But the range was $5,000 to $145,000. That completely describes a different distribution, doesn't it? Right? Right? Not to mention, so we're interested in what would we consider the center of a distribution. We're interested in how much variation is there within that distribution, right? We're interested in the shape of that distribution. We're looking at this and going bell-shaped, 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 bell-shaped. There's lots of shapes out there, right? Right? Tax returns. Do you think tax returns are bell-shaped?
No.
No, I don't either. Right? Right? I think a vast majority of tax filers get a relatively small return, and then there are a couple rich people who get a huge return, right? I don't think that distribution looks bell-shaped at all. In fact, I think that distribution probably looks, whoops, is that what it looks like? No.
That's exactly what it doesn't look like.
That's exactly what it doesn't look like. You see what I mean, right? Right? So we're interested so you notice that there's more to the question now. Now, not only are we interested in being able to generate actual probabilities, but we also want to look at that distribution as a whole, right? Please.
If this is a good transition point, could I talk about can I ask some questions to get a little bit of clarity on what you have on the screen here?
Try.
Underneath the capital sigma over summation thing, you have omega is in the range of sigma. You said it in English in a way that was like comprehensible to me, and then
I wrote it in math.
Yeah, I was writing something else and I didn't have a chance to actually catch it. So In this case,
Right?
I know
Don't forget that a random variable at its original core is a mapping from a sample space to the reals or to numbers, right? And so the probability that x is some particular value is the sum of the probabilities of those outcomes that map to that value. Right?
Okay.
For instance, y is the probability that x is 1, y is it 3/8? Because it's 1/8 plus 1/8 plus 1/8, right? So at its core, there are those outcomes, it's mapping, it's thinking back to those outcomes. Does that help with that?
yes, what in this example would be omega then?
What's that?
What in this example would be omega? I can see little x, I can see big
Oh,
X.
little omega right there?
Yeah,
TTT is 1,
okay,
right?
okay.
Right?
I see.
So is HHT,
Okay,
right?
yeah.
Right? Does that make sense? Does
That
that make
helps a
sense?
ton,
See,
yeah.
in fact, that symbol, that kind of cursive E means is an element of, right? So
Yeah.
these are the outcomes that are elements of the sample space.
Sick, thank you.
Nice. Okay, fantastic. Okay. Next notion, okay? When we consider a probability distribution, right, we may be interested in, among other things, the center of the distribution. Center of the distribution. What's a typical value, right? If somebody told you I just graduated and I got a job and I'm making $120,000 a year, is that a typical value or is that an outlier?
Very much an outlier.
Right? I don't know. You know,
Well,
I've been out of the workforce for so long, right? How much variation is there?
Oh,
How much variation? Right? 3, the shape. Right? Different shapes have very different consequences. Okay? In fact, a lot of ways, that's one of the most profound ways that probability statistics gets misused.
just thinking about that thing you were saying about the mean of like salary.
Mhm.
Why do websites like a statistic bureau usually display median instead of mean?
Because they provide different bits of information, okay? And so let's talk about that in a little bit. But a mean like is a, you know, particularly with a finite number of values, like for a sample, it's simply how many values you've got. I mean, the sum of all your values divided by how many you got, right? The median, on the other hand, ranks those values and plucks out the middlemost, right? So you take a distribution like this, okay? Okay? You take a distribution like this where the vast majority of the values are down here, but you've got some very large values up here, right? These very large values are going to pull that average up, but they're not going to affect the median. You see what I mean?
Yeah.
And so particularly when you get non-bell-shaped, non-symmetric distributions like this one is, those two measures give you dramatically different or different interpretations, you know? And the way I like to think, and we're kind of ahead of the game here, but the way I like to think about it is an average is a valuable number because it gives you this sense of the whole, and it's related to here. We'll talk more about that in a bit. But at the individual level, the median might be more valuable, you know? For instance, take those refunds. Because there are a couple, you know, because there are those rich folks on the hill who get tens of $1,000s in refunds, the average refund might be $2,000, but the median refund might be $500, you know? So that median is probably a little more representative of a random individual than that average is. That's why you start seeing, and that's why you're not hearing me say words like means and medians. Rather, I'm being very generic. What's the center? You know, like what's the center of a bell-shaped curve, like this or this? Everybody's in complete agreement. What's the center of something like this? I don't know. You know. And so that's why you have these different measures. Fantastic, good job. The other thing that I should add here, because it really is consequential, in fact, we just talked about averages, and we saw that, or at least we said that large values up here are going to have this tendency of dragging that average up, right? So that means that if you have any outliers, they're going to be particularly affected, the average is going to be particularly affected by it, right? So knowing something about outliers is also worthwhile, because don't forget, if you design a circuit and it's got these components in it, you know, the normal components aren't going to make your circuit fail. It's the outlier components that are going to do it to you, right? And so, let me see. Again, continuing with this maybe simple example, the cumulative probability function. In our book, we'll denote that universally as a capital X subscripted by whatever the name of your random variable is. Oops, I apologize for that. Back on, there we go. Okay. And a cumulative, okay. The cumulative function is the probability that x is less than or equal to that little x value. Right? And so maybe I'll make up another example, just because I'm sick of the coins. Example, right? Random variable x has the following probability distribution. Okay. Let's say that x can be 10, 12, 14, 16, 18, or 20 with probabilities, and I'll make those little x's with probabilities. 0.3, 0.2, 0.15. What am I up to? Point 1. Okay. By the way, what am I doing in the back of my head here?
Totaling to 1.
Totaling to 1. Good job. 50. What am I up to? 75. Shoot, that is okay. Kind of. Maybe I'll make that a. No. Yeah. 15. Okay. 1, 0, and 30, 60, 80, 1, 0. Okay. Right. Fantastic. Did I create a probability distribution? Yeah. Okay. So we confirmed that they're all non-negative and they sum to 1. That's all that question was asking. And so, for instance, by the way, the probabilities add to 1, right? So in other words, what's the probability that x is equal to 12? Well, that's 0.2, right? What's the probability that x is equal to 13? 0. We're happy with 0, right? Because don't forget, we've consumed 100% of the probability on those even integers right there, right? Is 0. Okay. Good. And so you see that there's this kind of a spike going on, right? It's kind of, what have I got there? 10, 12, 14, 16, 18, and 20. Probability 0.3, 0.2, 0.15, 0.15, 0.10, and 0.10, something like that. Not to scale, I'm pretty positive about that. And there's a 0.10. Okay. Right. Definitely not bell-shaped. We could call this particular distribution where you see it tailing off to the right is called skewed upward. Okay? Skewed upward, skewed to the right, skewed positively, those are all synonymous for the same thing. Okay? This shape is skewed upward, i.e. positively, i.e. like I just said. Okay? And so on here, let's notice a couple things. Let's add this, where am I on this page here? Cumulative probability function. Okay? So what is the cumulative? Okay, is the probability that x is less than or equal to that particular value, right? So the cumulative of 10 is the probability that x is less than or equal to 10. And based on this table, what is the probability that x is less than or equal to 10? What did I hear there?
0.3.
0.3, yes, perfect. Is 0.3, and f of 12 is what is f of 12?
0.3 plus 0.2?
Oh, okay, otherwise known as 0.5. X is less than or equal to 12, right? It is 0.5. Okay, we happy with that? Right? Capital F of what's next? 14 probably is the probability x is less than or equal to 14. What are we doing? We're either just summing those up, or it's everything we accumulated up to 12 plus the new probability, right? So do you like a 0.65 there? 0.65, right? And so forth and so on. Of 16 is another 0.8, 0.9, fx of 18, fx of 20 is 1.0. Okay? How does that feel for us? We like that? Okay. And so, fantastic. Nice. By the way, what is the cumulative probability for any random variable? What's the cumulative probability associated with the maximum value in that list set of possibilities? Like in here, we just saw that the maximum x could take on is 20. The cumulative is 1, right? Doesn't that make sense, right? Because we've got all the x values that are possible there. We've exhausted all the probabilities there. The probability of being less than or equal to your biggest value better be 1, shouldn't it? Right? Yes, please.
I can see how this could be misleading or cause misinformation.
It does.
Because we looked at f of x of 10
Mhm.
is 0.3.
Mhm.
However, that does not encompass the fact that the only value x can take on in that set is 10. Like, it can't
Sure it
be
does.
9.
Sure it does. Can't be 9, right? Probability of 9 is 0. Right? Now over here I asked what's the probability of 13, and you correctly said 0. What's the cumulative function evaluated at 13? Be 0.5, wouldn't it? Would it be 0.5? 0.5, right? And so let's note here, continuing with this.
Assign phantom probabilities.
Continue with this. The cumulative of 13 is the probability that x is less than or equal to 13, which, by the way, is, since x cannot take on any values between 12 and 13, is simply the probability of being less than or equal to 12, right? Do we agree with that, right? Or the only way that x can be less than or equal to 13 is if it's either 10 or 12, right? And so I love that 0.5, right? If you look at the CDF, what do I see there, right? And so I've got a 10, a 12, a 14, a 16, an 18, and a 20, right? Well, right up until I get to, but not including 10, I'm just living at 0, aren't I? Right? Once I get to 10, let's see, there's a 1, there's a 0.5, there's a 0.3 right there. Does it not jump up to 0.3, and then it lives at 0.3 right up until it nearly gets to 12, at which case it jumps up to 0.5, right? Stays that way, okay, until it gets up to where am I, 14, it goes up to 65. You see what's going on here? Right. Up to 80, up to 90, up to 90, and then 1 thereafter, right? You see a couple things here, and I know this is a discrete random variable, but it's not quite as obvious as it might be. Did I draw something that's left continuous or right continuous? Or continuous?
I think it's just continuous.
I'll tell you it's not continuous. Right? It's not continuous because there's that jump there. Right? Is that right continuous or left continuous?
I guess right continuous then.
Right? No, don't forget. But if I approach 10 from the left, the limit is 0. If I approach 10 from the right, the limit is 0.3. Right? It's not continuous. Right? But we see as I approach from the right, the limit of 0.3 is equal to the function value. So it's right continuous. Right? All right? CDFs, cumulative functions, are right continuous. Functions are right continuous. Okay. Certainly in the context of discrete random variables where you have these gaps between the values where probabilities are 0. You also notice that the limit as x goes to negative infinity of a cumulative has to be 0, right? You also see that the limit as x goes to positive infinity of a CDF has to be 1. Okay. good, good. Let's tinker with this example here a little bit, okay? And so, more questions, okay, with this example. How are we doing? Oh, we're getting, oh, look at us go. Okay, another day's almost behind us. Okay, so let's see. Okay, what's calculate, find each of the following probabilities. Right? I'll say A, the probability that X is equal to, I don't care, 14. Right? So the probability that X is equal to 14 is my probability mass function evaluated at 14, and that's simply a 0.15. Right? And B, the probability that X is less than 16. What do you want to do for the probability that X is less than 16?
Use the complement?
Well, I mean, we only got 6 values there to work with, right? Which ones satisfy X is less than 16?
10, 12, 14.
10, 12, or 14, right? Is px of 10 plus px of 12 plus px of 14 is 0.65, right? That we made that too hard. Right? Do that last problem, but don't use the probability mass function, use the cumulative. The probability that X is less, don't forget, X can take on with positive probability 10, 12, 14, 16, 18, or 20, right? Cumulatives always include less than or equal to. So the probability that X is less than 16 for this random variable is the probability that X is less than or equal to what?
14.
14. Less than or equal to 14 is the cumulative, right? And the probability that X is less than 16 is the probability X is less than or equal to 14 is the cumulative of 14, or 0.65. Right? And by the way, problems are not going to remain this nice and simple. Right? Okay. C. The probability that X is less than or equal to 19 and strictly greater than 12. Right. What's that? Well, let me see. What values of X do you want to include in this? 14, 16, 18, we in agreement? Sure. Is px of 14 plus px of 16 plus px of 18. And again, he sighs because this is too much work. 0.4. Okay, that last question. Let me fold that paper. I still got 5 minutes. All right. That last question. Okay. Let's see. The probability that X is greater than 12 and less than or equal to 19, don't forget that X can take on, what is it, 10, on the number line here, 10, 12, 14, 16, 18, and 20, right? We want to include the 14, we want to include the 16, we want to include the 18, right? So, can't I take everything to the left of 19 and parse off everything under 14? right? Or in other words, it's the probability that x is less than or equal to 19 minus the probability that x is strictly less than 12. Wait, did I do that right? Wait. Did I do that right? I like the no. What did I do wrong?
You need to have the equal.
Where do I need to add equal?
To 12.
To right there, right? Because we're not including 12 here, which means we have to lop it off here, right? And so that is, that is the cumulative at 19, of course, but don't forget that there's no probabilities between 18 and 19. So it's the cumulative of 18 minus the cumulative of 12. Do you agree with that?
Yes.
Right? Okay. By the way, these tools, you notice almost automatically, rather than using the actual probabilities, you seeing me push us toward these cumulatives. These cumulatives are truly going to be your friend, right? Particularly when we get into continuous random variables. Right, so the cumulative of 18 was 0.9 minus cumulative of 12 is 0.5. Hopefully that's what we got before. By the way, could you use a similar argument to get the probabilities of a complement? Could you turn that into something that uses a CDF? Yeah, you absolutely could. So for instance, the probability that x is greater than 16, right? Which, by the way, again, we're starting out with simple examples, means it must be either 18 or a 19, so I hope we all think the answer should be 0.2, right? Is 1 minus the probability that x is, do you agree with that sentence? Right? If I'm not including 16, then I better lop it off here too, right? And so that's 1 minus the CDF evaluated at 16, or 1 minus 0.8, which is 0.2. Okay? Right? How's that feel? Set as kind of an introduction. And so we were talking about a midterm. And where we want to draw this line in the sand for next Wednesday's midterm, right here. Okay? So in other words, in understanding of random variables, probability distributions, and cumulative probabilities. Okay? We'll hone in on that next Monday when we're actually really talking about the midterm, but that's what I see there. Okay? How's that feel? Any questions, thoughts, concerns? Please. One-sided page of notes. One-sided page of notes.
Yeah, and the final is cumulative.
Yeah.
So a
What's
piece
that?
of paper, one side.
8.5 by 11.
Yes.
Yep,
We're gonna
that
do this
size.
for the final.
That size.
The final will
Yeah.
be double-sided.
How's that feel? Good for everybody?
Yep.
Fantastic. By the way, check out sometime very soon. I'm hoping it's as early as tomorrow. I'm going to post a big practice thing
Excellent.
in Canvas for this midterm. Okay?
Are the answers included to the
That's what part of what makes it humongous.
Okay, thanks, I appreciate it.
Yeah. All right.